Hello, my name is Erlin. It's very easy to remember. It's like Berlin without B. You can call me Erlin or Erlin. So I will talk about how to build AI while honoring subject rights. So first of all, I want to let you know that this wouldn't be a talk about using an AI to honor data subject rights. This would be a talk about designing AI and honoring data subject rights. So I work at Silo AI. This is a small company which was founded last year. My position there is the data privacy expert, but I also work in the machine learning team, and the purpose of Silo is democratization of AI, and Silo is an AI IT service company which is building tailor-made AI for different businesses in different industries. Okay, so when I said, I hope you can, the colors are not perfect, but anyways. So when I say while honoring data subject rights, what are these data subject rights? How would I define them? So I use GDPR as the framework to define these data subject rights. So these are the articles which I believe concern AI, which we should consider when we are building AI. And especially these three are the ones that we should directly consider. But these two are more that anyone will basically need to consider if they're working with personal data. So here are my solutions to the problem, to the challenges. So one challenge is that decision based solely on automated processing, that we have kind of the wrong perception that AI is equals to autonomy. My solution to that to have human in the loop. And the second one is explaining the logic involved in AI decision-making process. The challenge here is the complexity of AI models, and my solution is using model interpretability techniques to tackle with that. And the third one is right to erasure. So the challenge here is that AI models can memorize the information in their training data, and the solution is using private learning approach. So let me start. So I said that we have kind of this wrong perception that AI equals to automation, autonomy, but the ideal AI system that would make sense to design and use in real life is actually machines plus humans. So how we can make this happen? So let's look at this framework. So you have your data, and you're trying to find some patterns. You are trying to develop your AI model. So when you're sure your model is working, then you decided to deploy it. So when you deployed it, there will be new data coming to your model. So your model, you can improve your model with new data. So then you're using this model to tackle one problem, and your model is giving you some predictions. And here, there is a human here who will look at the signals, AI predictions, and make the assessment if that makes sense or not. So imagine you're using Google Translate and there's wrong translation. So you can correct the translation, and what you do is basically you give feedback to your model. So your model will learning from its failure. So I put some nice use cases. So I think fraud detection, fault detection, and assessing documents, legal documents are good use cases. So about fraud detection, imagine, so AI can help you to tackle with many payment transactions, and AI can help you to assist you that what could be fraud. But then we have here the fraud analyst, who is the person to stop any transaction or not. So this person looks what AI predicts and decides if it makes sense to use it or not. So Fabio will talk about human in the loop more, so I'll skip this now. And the second thing that we need to tackle is explain the logic behind AI models. So I think I interpreted this in two ways. The first way could be that we need to explain people how AI models work. So for example, we have this neural network, we will explain what is a neuron, what are the layers, and how like these neurons work, and then what functions we use there, and so on. I think this is not the purpose here. I think this is quite boring for many people. I think the purpose here could be more that explaining the reasons behind the predictions of our AI models. So, for example, let's say that my model is predicts that this woman wouldn't like Brussels sprouts, and this man would like Belgian beer. Okay, this makes sense. So, but if I want to know why my model thinks like that, I need to tackle with something like this. Actually, this is a very, very simple neural network, and which only has 3 layers and doesn't have very fancy operations. But even some very simple neural network, I need to have like those many weights that I need to calculate, and I need to understand how my model came up with this decision. This is quite complex for any human to understand what those weights mean. So how can we explain predictions when hundreds of values are involved in our AI models? And is there actually any way that we can interpret AI models? So when we look at this chart, we see here, so I hope you can see here is interpretability and here is accuracy. We see that there is an inverse relationship between interpretability and accuracy. So when I have simple models, they are more interpretable, but when my models get more complex, they get more accurate but less interpretable. So it's hard to explain complex models like the one I showed you, even a very simple neural network. It's hard to explain that. So I put the first 2 questions above, and the third question is how we can actually make sure the prediction made by a very complex black box model actually is reliable. Can we trust these predictions? So there are some techniques in order to tackle this problem. So how they try to solve this problem is that they don't try to explain the whole model, they try to explain just one prediction that you're trying to understand. So these are these 2 techniques that I have tested. So for example, imagine you have this AI model and it predicts that this person has flu, and it shows you the reason that because this person has sneeze, this person has headache, but this person have no fatigue. So the human can look at here and assess if this makes sense or not. This is a very good example of human in the loop also. So I will talk about this shop, which is the one that I'm using. So for example, I took this League of Legends dataset game and I try to predict if a player will win the game based on their performance measures. So this guy here, my model predicted that by 95% probability this guy will win the game. And my model predicted that by 3% probability this guy will lose the game. So with SHAP, basically what it's showing that why I came up with this number. So the red ones are showing that to me that these are the effects that made my model to move to this number with this magnitude. And these blue ones are the ones who affected it negatively and to make my prediction to move like more to the 0 side, more close to the 0. So here, like I have this, for example, gold earned per minute is like 451 gold, so this is a quite high value. Anyway, so let's look at this scenario here. So here, because I'm predicting that this guy will lose the game, I see most part is blue. So these variables are pushing my model to decide that this guy will lose the game, and these are pushing that this guy will win the game. So for example, if I look at the golds, here I see 451, and here I see this guy earned 187. So this is a pretty low amount compared to this. Okay, this makes sense because this guy earned more gold, so he would win the game. This guy earned less gold, he would lose the game. So the human can basically assess if these numbers make sense or not. So there is another example with computer vision. So I was using this inception tree, one of the most famous computer vision algorithms, to basically understand what this image is. So my algorithm told me that this is an Eskimo dog. This was my algorithm's first prediction. My algorithm's second prediction was this was a Siberian Husky, and the third one was it was a dog sled. So then when I use SHAP, I see that for this image to be an Eskimo dog, the explanation is all over the place. But when I look at this, my model's second prediction, the explanation is on its face. So even though this is the second prediction of my model, when I use SHAP, I can say that, yes, this makes sense because my model is making this decision by looking at this dog's face. So let's go to the third topic, which is erasure. So I said that when a machine learning's model are like learning from their training data, you build the parameters with what there is in the training data. So especially in deep learning, the deep learning methods have tendency to memorize their training data, information about the people in their training data. So, for example, you are just a subcontractor, you just build AI model for some controller, and then you need to erase the data. But if you want to still keep using that AI model that you built, there are ways that from that model you can reverse back what was in your training data and learn about the people in the training data. So this is not a good thing. This is something that we definitely need to tackle. So I guess most data scientists first will say, let's use regularization technique. So by using regularization technique, you avoid overfitting to your training data and you try to generalize your model. But there are research which shows that these regularization techniques are not enough in order to tackle this memorization problem. So what are the ways? So there is this new approach called private learning. Can we learn privately from the training data? There is this approach called differential privacy. So we can apply this differential privacy to machine learning models, but I'm just going to explain you how it works in a very, very simple way. So in differential privacy, we think that there is a trust boundary, and here there is no human, and here there is human. So I have my data here where there is no human. So a human can only access to that data by making some queries, by asking something about the data. So, but when I'm giving answer to that query, because I'm using a differential private mechanism, I would add some noise to the answer. But the calculation of this noise process is, I wouldn't go into detail, it depends on the query. So you want to add noise in the way that you can hide the information in the most sensitive person in that dataset. So here, for example, I'm asking what is the average salary in this room. So I got my one answer, and I remove Reggie from this dataset, and I ask the same thing, what is the average salary? So if I have the two answers, I know what is Reggie's salary, right? So if I use this technique, because I am adding noise from this Laplace distribution in order to prevent that anyone who gets two answers to this query, like this is the dataset with Reggie and this is the dataset without Reggie, there is no way that this guy can find out what was Reggie's real salary. So this method gives me this mathematical guarantee that there is no way to trace back to that person. So the idea here is basically the answers are not dependent to any person in the dataset. That's the idea. There is no way to trace back to the person. So for example, here there are two interesting terms. So one term is this privacy budget epsilon. So for example, you also need to decide how much private you want to be and how much accurate you want to be, because privacy and accuracy don't go together. So if you want to be more private, then you need to add more variance, and you need to like perturb the answer more. But then, okay, if you have so many queries, then this will kind of not work very well with your, this will influence the performance of your machine learning algorithm, basically. But so also like this is a guarantee. So like don't think like I'm asking one question. This is basically a guarantee that even though I'm asking like 1,000 queries, like 10,000 queries, like here are the parameters to help me tackle with that. There is no way to trace back to the answer. So there are like something, like I need to decide how much secure I want my answers to be. So here, is it finished? Okay, yeah, I'm also done. Yeah, so so the idea is basically, this is the distribution with Alice and this is the distribution without Alice. So by changing the, like by adding or removing one person, the answers shouldn't be that different. So it wouldn't also affect my results that much, but it would give me privacy guarantees. So thanks for your